Hey guys, sorry to be gone for this one. This is lesson 3.3, the addition rule notes. Hopefully you have the guide notes in front of you that the sub gave to you. I'm going to fill those out. It should go pretty quick. Most people do better with the addition rule than the multiplication rule, what we just finished in 3.2. So hopefully listen to the notes, getting the notes down, and then the next 2 days of practice can help you out, and then I'll be back on Monday to go through it with you. So we're going to talk about being mutually exclusive and not mutually exclusive because that relates to how the rule applies, and then we're going to actually use the addition rule. Mutually exclusive is when basically your events cannot occur at the same time. If there is overlap between your events, then they are not mutually exclusive. So for example, if we're going to be talking about the event of being a child and being 7 feet tall, mutually exclusive. You will have nobody who is both a child and 7 feet tall, or maybe under 5 and 7 feet tall, or something like that, something that cannot happen at the same time. But if we're going to talk about the event of being an adult and over 7 feet tall, there will be some people that are in both events here. If there's overlap, they are not mutually exclusive because the events can occur at the same time. Or maybe we could talk about the events of like pulling a card out of a deck of cards and getting a red card for event A and getting a heart for event B. There are definitely ways to be in both events. So if I was in class, I'd ask people to raise their hand if they're a female, and then I'd ask people to raise their hand if they're future nursing majors. We're assuming that these are not mutually exclusive because I'm pretty sure there's at least one of you in here who is both a female and a future nursing major. If there's overlap between the events, they're not mutually exclusive. But if I was going to look for the event A of being a male blood donor, probably some of you guys in the class, and then if I'm going to talk about being a sand volleyball player, probably isn't any male blood donors who also play on a sand volleyball team. There might be, I could be wrong, but usually in the past that's been an example where I'm not going to find anybody who's in both events. So what that means is when we do the addition rule, it's for when we want event A or event B. We don't care which it is, as long as one of them happens, we're happy. So they'll say P of A or B, and that'll be found by the sum of the probability of A plus the probability of event B, but we're going to subtract out the probability of A and B. Because if we're just adding up all the people in event A and then all the people in event B, you might have just counted 2 people twice. So we're going to subtract out anybody who appeared in both so that we're not double counting people. So that means if they're mutually exclusive, if there's nobody who's in both events, then you could just add up your individual probabilities and not worry about it. This can be extended to any number of mutually exclusive events, which just means if I want the probability of A or B or C or D, you could just keep adding. So that means if I'm going to be selecting a female from this class or a future nursing major, let's say that out of our 35 students in our class, 21 of you guys are female. We're going to pretend that 3 of you are future nursing majors. One of the males in the class is a future nursing major as well. So if I want the probability of selecting a female or selecting a nursing major, we need the probability of selecting a female, 21 out of 35, plus the probability of a nursing major. Well, 3 are girls, 1 is a guy, so 4 out of 35. However, we just counted 3 of you guys twice. 3 of you were in the female group and in the nursing group. So we got to take you back out. There's no reason to count somebody twice. It inflates your probability. You're going to get 22 out of 35 for that. If you are ever doing an OR probability and you notice that you are changing denominators and it's not because you reduced or anything like that, you're doing it wrong. You should always have the same denominator because it's not like an event is happening and you're reducing the number of people. It's just at the beginning, how many ways are there to do this? So then if I changed event A to selecting a male blood donor, and event B is selecting a volleyball player. I got rid of the whole sand volleyball playing team, but whatever, just a volleyball player. Let's say 35 students in the class, 7 of you guys are male blood donors, 2 are members of the girls volleyball team. Which means if I want either of those events to happen, there's 7 guys out of 35, there are 2 volleyball players out of 35. There's nobody who's both a male blood donor and a girl volleyball player. So there's no overlap, we just add them together. If they're mutually exclusive, there's nothing to subtract. So then, if I want to select a card from a deck of cards, I want the probability of finding a 5 or a queen. So for OR probabilities, we're going to sum the individual probability events. So we're going to have the probability of event 5 plus the probability of a queen. We don't have anything to subtract because there's no 5 queens. Like there's no queen of 5s or anything like that. So the probability of selecting a 5. There are 4 5s in the deck out of 52. Just like there are 4 queens in the deck out of 52. Summing them together gets us 8 out of 52 or 2 out of 13. So on any draw, you have approximately 15% chance of getting either a 5 or a queen. If instead I wanted to find the probability that the card is a face card, something with a face on it, a jack, queen, or king, or a heart, I don't care what happens, but either one is what I want to count, then we're going to have to find the probability of a face card. We're going to have to find the probability of a heart, but we're going to take out the overlap because there are some cards that are both. So of all of our face cards, jack, queen, king, if there are 3 types of face cards and 4 suits, there are 12 cards that are face cards out of 52. Why do I have 16? Huh. That's a typo that I've never noticed. I've used this in previous years and I didn't notice that. Sorry about that, guys. That should say 12 out of 52. 4 jacks, 4 queens, 4 kings. So unless I'm not thinking properly this morning, that should be 12 out of 52. So then the probability of a heart, well, there are 13 of each type of card, so that should be 13 out of 52. But there are some heart face cards, some that just got counted in both groups. There would be the jack of hearts, queen of hearts, king of hearts. Wow, that's wrong too. That's weird. Either way, if we actually add it with correct numbers, not the numbers I'm about to display to you, that should be 22 out of 52, not 25 out of 52. So it should be 11 out of 26 is the reduced probability. My slide is wrong here. Sorry about that. Let's go to one that hopefully is right. If we have an 8-sided die, numbers 1 through 8 are going to be rolled. I want the probability that the roll results in an even number or a number bigger than 6. So I'm going to be summing those together, but subtracting any overlap, any number that's in both events. So of the numbers 1 through 8, 2, 4, 6, 8, 4 of them are even out of 8. Of those numbers, 7 and 8, 2 of them are larger than 6. But there was a number that was in both. The number 8 is both even and greater than 6. So there's 1 out of 8 rolls that would be in both events. So you got to subtract out the overlap since they are not mutually exclusive. 5/8 would be the probability of that happening. So then if I say 12-sided die, find the probability that the roll results in an odd number or a number less than 4. So we're going to sum those together, subtracting out any number that's both odd and less than 4. Half of them will be odd, and then 1, 2, 3 are less than 4. But the number 1 and 3, those two numbers are both odd and less than 4. They're not mutually exclusive. Subtract it out. 7/12 would be your probability. Like I said, most people do better at this than the and probability, especially since we're not going to deal with a lot of two-way tables. It's more scenarios like this. I could give you a pie chart. This is just giving the probability, not the probability, the empirical probability, the empirical frequency, relative frequency is another way to say it, for each of these results being reported by a new mother. And we want to say the probability that she would say that it's the same, that the difficulty level was the same as what she expected, or more difficult than what she expected. So this blue region is more difficult than what she expected. Excuse me. The green here is about the same of what she expected. There is no way to say, oh, that was more difficult, but it was also the same. So it's either or. We don't need to subtract out anybody. Nobody was in both events. So the probability saying it was the same was the 31%. The probability saying it's more difficult is the 13%. So 44% of women said it is either the same or more difficult than what they expected. That's all. So you can spend the rest of the time working on the practice for this. Talk to each other, help each other out, because like I said, I'm not back till Monday, and that's a really long time to wait to get your questions answered. So definitely make note of which ones that you as a group cannot answer. Check the odds in the back of the book. Do whatever you need to do, and I'll see you on Monday.